So our next task is to transform this equation into a time domain. In other words, we want to find the inverse Laplace transform of this term. And we will do this using partial fraction expansion.
All right, let's actually have a look at Margaret's problem. Now, this was a solution that basically was performed by taking a Laplace transform. So it's a solution that's actually in the S domain. Now, what we want to do is really convert this back into the time domain using tables. But the form that this is in doesn't lend itself to really those tables. And so what we really need to do is express this term in relation to its partial fractions. And so what is this? This would be equal to a constant K1 divided by the S plus 4 plus a constant K2 divided by S plus 2 plus a constant K3 divided by S plus 3. All right, our next step now is really to multiply both sides by what we have in the denominator here. So this side gets multiplied by this side gets multiplied by this. If we do that, what we end up with then is a 2s squared plus a 20s plus a 45, and that's equal to the K1, and that is multiplied by s plus 2, s plus 3, plus a K2, which is multiplied by the s plus 4 and the s plus 3, and finally the K3, which gets multiplied by the s plus 4 and the s plus 2. All right, so that's the expression now we're going to work with in order to find these constants K1, K2, and K3. All right, so let's see if we can evaluate the first K1 term. So what do we want to do? We want to actually zero this term here, and we want to zero this term over here. So how do we do that? Well, let's have a look at what's common in both of those terms. Well, it looks like an s plus 4, doesn't it? There's one here and there's one here. So what we can do here is make s then equal to a minus 4, and we're going to put that information now into this equation, which means that this term goes away and this term here will go away. So let's do this. So what we have is 2, and I'll put a bracket here because this is a minus 4, and we're going to square it, plus a 20 times a minus 4, plus a 45, and that is equal to what? It's equal to the K1 term. Open a bracket here, maybe a big bracket, and we've got what in here? We've got really a minus 4 plus a 2, close that bracket, and that's multiplied by a minus 4, and it's plus a 3. We close that bracket like so. All right? So that's what we've got. Now, if we work this a little bit more, what we'll find is that we've got, and I'll do that, we've got a 32, and that's minus an 80, which is that, plus a 45, and that is equal to, and if I evaluate this over here, I get that's a 2K1. So we're now in a position to very quickly find K1, and K1 is actually equal to a minus 3 upon 2. So that's our first constant that we found. Now we want to actually evaluate the K2. So how do we do this? Well, once again, we've got to zero this and we've got to zero this. What is common to both of these? There's an s plus 2 here, s plus 2 over here. So really, if we make s equal to a minus 2, and we put that into this equation, then we'll find that what? This term here is going to go, and this term here is going to go. So let's do that. So we have what? A 2 s squared, so that's a minus 2 squared, plus a 20 times s, which is a minus 2 for s, plus a 45, and that is equal to this K2 now. I'll open up a bracket, and we've got what? I'll open up another bracket here. So we've got what, a minus 2 plus a 4, close that bracket. And then over here we've got a what? Minus 2 plus a 3, close that bracket like so. All right, so let's take this just a little bit further. This comes out to be what? 2 2s are 4, 2 4s are 8. So this is what, an 8 minus, this would be what? A 40. And then plus the 45. And that is equal to, well, if we kind of work this out, what it comes out to be is really just a 2k2. All right? And so really k2 is equal to a 6.5, or if you wanted to express it as 13/2 to match what Margaret has in her work, we can do it that way. All right, so that is my second constant for k2. All right, we now need to evaluate k3. So we want to make really this 0 and this 0. So what's common to this and this? Well, it looks like s plus 3 is common. So really what I want to do now is I want to make s equal to a minus 3 and put that into this equation. That will 0 this term and 0 this term over here. So we have 2 times a minus 3 squared plus 20, s being a minus 3, plus a 45, and that is going to be equal to k3, and I'll open up a big bracket here. S is what? Minus 3, and that is plus a 4. Close the bracket. Open up a bracket. S is what? Minus 3 plus a 2. Close the bracket like so. So everything can now be evaluated here, and we find out that k3 is actually equal to a minus 3. All right, so if I now wanted to actually express my y of s as partial fractions, y of s then is really equal to what? It's equal to the first constant, which is the k1, so that's a minus 3/2, divided by the s plus 4, plus the next guy, which is the k2 over here, which is a 13/2, divided by the s plus 2. And then finally, I've got my minus 3 divided by the s plus 3. All right, this can now be operated on by using tables to perform the inverse Laplace transform.
Now, looking at the tables, the inverse Laplace transform of this first term is minus 3 onto e to minus 40 u of t. The inverse Laplace transform of this term will be 13 onto e to minus 2t u of t. And the inverse Laplace transform of the last term is minus 3 e to minus 3 t u of t. Okay, and in the final step, I'll just take the u of t out of the bracket, and we can say that this is our final solution. We have found the solution of our differential equation. It is a function of time, which is given in this form.